All right, it's 5 o'clock, so I'm going to begin introducing our next speaker. Today we have Timothy Lucas presenting on Slopes, the app. Um, yeah, go ahead and take over from here.
Thanks. Uh, Thanks to the organizers and for Brian Winkle for inviting me to talk about slopes again. I'm just going to let you know that about 15 minutes ago, we had an earthquake here in California. So if the room starts shaking, you'll know why. I wanted to talk to you guys about an app that I use in the classroom called Slopes. It's something that we've developed with myself and students at Pepperdine University. And so if you're interested in just kind of playing with the app while you're listening to my talk, you can go to slopesapp.com and you can get a copy or you can get a link that'll take you to your preferred app store. So the app is available for both iOS and Android. And so you can download the app for your phone or your iPad. Also, if you happen to have a newer Mac, then you can also download the app. So I just always tell people that we've now kind of been around for a little bit with the app. It's a project that I worked on with students, and so I've just kind of been building it up so you can kind of see that over the years we've added not just activities to the app, but also we've added various devices to the app. So I'm gonna just talk briefly about why am I using mobile devices in the classroom. So let me see if I can, there that is. Okay, so why am I using mobile devices in the classroom? A while ago, back in 2010, the first iPads came out, and they at Pepperdine purchased a bunch just to see what they could do with them educationally. And so a colleague of mine and myself, we ran a little study of using iPads as spreadsheets and also as graphing calculators, like in our classroom. We found that the devices were portable. They have comparatively large screens, so they have kind of bigger screens than, say, your graphing calculators, and they have this tactile interface. And so we learned that students were more willing to share with each other and to collaborate on a single device when they were using these kind of tactile devices. And so that inspired me to actually write the app for differential equations. And so we did a classroom study of that as well. That was published in Primus in 2022. And that's something, my wife is a science educator. And so the two of us published a paper together about a study that we ran on slopes for those who are interested. So before I talk about slopes, I like to talk about the classroom approach that I have to differential equations. I will say that at Pepperdine, we don't have an engineering school. And so the audience for my class tends to be not just math majors, but a lot of mathematics minors whose majors are in biology, chemistry, physics, economics, business, and a few others. So it's kind of a different audience than, say, a typical school that has an engineering program where you have a lot of engineers taking differential equations. And then also because we're a smaller school, we have a prerequisite of linear algebra for this class. So the students are a little bit more familiar with kind of matrices and things. But when I teach differential equations, I really like to start not with how do you solve an equation, but start with physical assumptions so that we can explore some applications in some of those areas that I just mentioned. So start with those assumptions, turn those into mathematical expressions so that we can then have some models that we can look at. And then I tell my students, like, you really want to think before you solve. You want to look for equilibrium solutions for your differential equations. You want to do some sort of graphical analysis, plot slope fields and phase planes, and you also want to look at possibly numerical solutions. And kind of look at all of those pieces before you kind of go to the analytical solutions. And that's because once we kind of move beyond the first order system, or just first order equations and then first order systems that are linear, there's a lot of stuff that just can't be solved. So I want them to think about the other pictures when we're looking at this class. So so I'm going to actually kind of tell you about two things during this talk. One, I'm going to kind of show you a progression of some models that are focused on some local ecology, and that's kind of to give you a sense of how I use the app in class. And then I want to kind of finish up with some semester projects that the students do for modeling, and kind of how we use slopes for those semesters projects. So before you I have like a California newt. These are local amphibians. They're species of special concern. And so they're in the creeks in Malibu and near Pepperdine. And so this is something that some of the biologists study. And one of the big problems that they have are invasive crayfish. So they have these crayfish that are not native to Southern California, and they have kind of overtaken the creeks, and they threaten the amphibian life there. And so one of the things that they try to do is try to see if they can trap a bunch of these crayfish so that they can possibly help out the local amphibian population. And so this is going to be something that I'm going to talk about a little bit. So I'm going to talk about a little bit of crayfish models that we do. And this is kind of just like a progression of simple models that I can talk through with my students, and we can think about so that we can look at pictures and slopes. So we have crayfish that they experience just kind of normal exponential growth. We also can look at crayfish that are experiencing growth, but maybe we have some sort of constant removal where we're trapping a certain number of crayfish like every month. Then you can throw on, say, a logistic growth model so that the crayfish don't grow without bound. And then I have two different kinds of models for removal for crayfish from a system. One with the logistic growth is just, again, constant removal. And then the other one is removal that's proportional to the amount of crayfish. So suppose you've trapped a bunch of crayfish, and so the crayfish population is quite low, then you won't be able to actually trap that constant amount. Instead, maybe you'll be able to trap a percentage of the population. And so these kind of have some nice features that I like to look at. And then through this, while I'm talking, I'm going to talk about a theme of bifurcations that pop up with the crayfish models. So bifurcations occur when there's a small change in a parameter value that leads to qualitative change in the long-term behavior of the solution of a differential equation. Okay, so having said all that, I'm now going to open up slopes. So this is the slopes app. This is the slopes app. This is the way it looks on my iPad, but it looks slightly different on your phone. And so there are 5 activities. So having to deal with slope fields and phase planes, plotting systems of equations. So second order equations form oscillations, and then something about numerical methods. So I'm just going to open up the slope fields activity. Something that you should see when you open it up is that immediately there's an equation that's there, and there's a slope field that's there, and that's so that students can immediately kind of start playing with a model when they're first opening up the app. So I'm going to actually change this equation from what was initially there to some sort of exponential growth equation. So So I'm going to edit that, and then I'm going to put in a parameter that shows growth, okay? And then immediately, once I have that first model, I start asking students questions about the slope field. I want to know, like, what do the arrows represent here? Like, so that, you know, they understand that the arrows are representing kind of the slopes of tangent lines for our solutions. I ask them to look for patterns. So oftentimes they'll get that there's a pattern here that if you move your eyes horizontally, you'll see that the slopes don't change as you move across horizontally. But as you increase y, which is increasing the population, then the slopes increase. So that's increasing the rate of change. And so I'll follow up with things like, how do the patterns that you see relate to the differential equation and the model? So hopefully they can make sense of, like, okay, steeper slopes make sense when you have more population. And then I often ask them to add like solution curves to this model. So they'll be able to just kind of tap anywhere in the slope field, and that'll add solution curves. They start to see relationships that the solution curves seem to follow those slopes. You can see that the slopes end up being tangent to those solution curves. And that just gives them kind of this basic understanding of slope fields when they start. I often then move to things like exponential decay, but for now, I'm gonna move on because I'm gonna focus on kind of what would be the crayfish model. I ask them about equilibria as well, but first I want to like add some sort of trapping to this. So I'm going to subtract a value, and you could put numbers in if you want, but I like to make my numbers parameters so that you can kind of use the sliders to change like what the parameters are in your model. So here we could have exponential growth, as you see, but some sort of constant amount of trapping. And so here you can see that I ask students questions about, like, does the behavior of the solutions depend on the initial condition? Okay, and so they can see that there's some sort of threshold where if you're trapping a certain amount, then if you trap for a given fixed trapping amount, depending on what the initial condition is, either the solutions will go to infinity or they'll die down and they'll go to zero. It's kind of nice because I asked him about like how this model relates to the one that they had seen before, where b was 0. So let me see if I can get it to be 0 for a second. And then they can ask questions about like how the equilibrium solutions have moved. So once you add some sort of trapping to the equation, then you can see how the equilibrium that you have kind of has moved from 0 off to another point. And then ask them things about like stability of the equilibrium and stuff, and things that they can observe with the slope field. Okay. So from there, like, we usually move on to something that's like a logistic equation. So I could type in equations by hand if I want, but also there's kind of some preloaded equations. So you'll see that there's some there. So a logistic equation happens to be preloaded here. And so again, like we talk through some of the assumptions for this model and how like you might have a population that starts with exponential growth, but as you get close to some sort of carrying capacity, then of course the solutions approach that carrying capacity. If you're above the carrying capacity, things approach the carrying capacity. We like to talk about the equilibrium for this problem. So there's an unstable equilibria down towards 0. And there's a stable equilibria that's at the carrying capacity. But again, it's just getting them used to these kinds of models, like looking through the progression and then seeing like how do the slopes change with these particular models. I'm going to add, let's see if I can do this. I'm going to add a constant rate of removal. I'm going to call that C. It's constant rate of removal. And then I'm going to, let's see. So if I start with C equals, say, 1, let's see if I can get this picture to be right. Okay, so So I'm going to have a constant rate of removal for these crayfish. And you'll see that depending on the initial condition, if you're above a certain threshold, then you're going to end up with the crayfish growing to a carrying capacity. But if you're below that threshold, if you're kind of down here, then you're going to see the crayfish population is driven out. If you increase that trapping amount, you'll notice that for any initial condition, that you're able to drive that crayfish population down to 0 with the trapping. And so that seems to be that there's some sort of change in behavior, that bifurcation point that I was talking through earlier. And so I might have students go through and like kind of vary the trapping to see if there's a point at which we see some sort of change in behavior, a bifurcation. And so it's hard to pinpoint just with the slider, but I think it's 1.25. You'll see here like that you end up with kind of a semi-stable equilibrium where solutions are going down toward it above, but then below it, they're going down to 0. And so this is like a first example of kind of a bifurcation point here, where if you're just below, you have 2 equilibria, but if you're just above, then you have no equilibrium values. So at the bifurcation point, you just have 1. And so this is something that they can explore, and then there's a realistic application to go with it, that there are people out there trying to trap these crayfish, and they need to know kind of how much they need to trap, say, per month in order to drive the crayfish population away. And then you can do the same thing with a proportional harvesting, like a proportional harvesting of the crayfish. I'm looking at my time and I'm thinking I'm going to leave that for now, but I can talk about it later during the discussion. So the second thing that I really wanted to talk about with slopes is that we in our differential equations class like do semester-long projects. So our goal is to understand and analyze a mathematical model using techniques learned in class. So the students, they form into groups of 3 to 4, and we try to get them to research mathematical models in the literature, or maybe even propose their own, depending on like some of the ideas that they have. And then what we want them to do is analyze those models that they've found or created using those techniques that we learned in class. Things like slope fields and phase planes, equilibrium analysis, numerical and algebraic solutions, just and all the tools that are available to them. And then they end up creating a poster that's kind of inspired by the posters that I've seen at some math meetings, like the joint math meetings. And then we have math and science faculty who come in and they kind of judge a little poster session during our final exam period. And so one of the things is that they use slopes kind of as their main computational tool a lot of the times. So I'll show you an example of what these posters looks like. Basically, we had some students, or we had some mountain lion sightings near campus. And so students were like, what if we had a predator-prey model where we had mountain lions and deer? And so they were first just kind of looked at a general predator-prey equation. And then then they thought like, okay, well, how can I change that general equation to something that's kind of a new kind of model to explore? And so they looked up what are called density dependent kind of predation terms. And so they explored this model and looked at kind of the phase plane and things. I'm going to show you what their phase plane looks like. So they produced some images and slopes. They could see that there's some sort of sink for an equilibrium value. So they did some analysis where they found a Jacobian for that system. And then they looked at the eigenvalues and saw that they were both negative. And so they had some sort of stable sink. And then although I didn't show you the phase plane activity yet, like you can kind of tell like it's the same kind of thing as a slope field activity where you could plot the where you can plot the phase plane and then and plot solutions on it. So this is the kind of stuff that they'll do in the midst of their projects.
We didn't go out. We can have a walk
So
with Liza.
Another example that I have, students were looking on modeling tumor growth. And so they looked up some papers about some various tumor growth models. And again, I'll kind of zoom in on one of their pictures. So you can see here, like this is kind of showing the picture of the model that they came up with. And so they took the words and they turned it into the equations, which I kind of, this one's kind of really pretty. And so I like to show it. And then again, they have, here's a phase plane that they have. And they made some conjectures because they could look at this phase plane and say, well, that equilibrium looks like it's a spiral sink. They have pictures from the phase plane, both of kind of immune cells versus T cells, as well as how those T cells and immune cells like evolve over time. And then I believe that they did do some equilibrium analysis. Like I don't think all of it's on this poster here, where they were able to find a spiral sink point. That they were there. And then if you were, I think that if you were dealing on the x-axis, or sorry, on the y-axis, they could find a saddle point as well, but that occurs when you don't have any tumor cells. I think I said T cells, but I meant tumor cells. They were tumor cells and immune cells. And then you can see that like, they like came up with a system of 3 equations. So they had tumor cells, immune cells, and normal cells. And one of the things that you can do in slopes is you can just put in a system of equations and it'll generate some solutions. So you see some of the pictures there. And they varied a parameter alpha 1, which was kind of an aggressiveness of the tumor. And then you could see that the more aggressive the tumor, the less kind of spiral sink behavior that you see. And then of course the higher level of tumor cells that you have. And then there's kind of more of a fight back and forth when you have a less aggressive tumor. And so that's some things that they looked at. Also had students look at like kind of an internal model of HIV. And so made a poster of that. And that was kind of fun because they looked at kind of a classic model of HIV where you had T cells, infected cells, and virons. And they, plotted solutions. And for one particular set of parameters, they could see that the infection really didn't catch on. But after that, they had that if you raise the number of virons that comes out of a bursting immune cell, then you get a kind of different behavior. And so they were able to locate a bifurcation point again. And again, they're just doing rapid prototyping of their models and being able to experiment. And then they're seeing things that they saw in class. So I always like talk too longs about things. So I'm not going to talk about the COVID model that some students worked on. But what I will say is that we survey the students after the class and we say, we ask them a question about whether slopes was helpful. So did slopes increase their understanding of mathematical models in their projects? And this is from one semester. You can see that most of them agree or strongly agree that that was helpful for them. Students say things like, it's good just because visualizing helps a lot to be able to understand, especially when you get to kind of higher levels of math and things kind of get hard to understand sometimes. And they like how interactive the model or the app is because you can move it around and manipulate it, and being able to click and see what does the solution look like. Anyway, I always acknowledge all the student programmers who were involved. So this is the list up until this point. And especially shout out to Joshua Haug, Jacques Jaubert, and Alex Prieger, who did significant amount of works on the initial program, the iPhone version, and then the Android version. And that's kind of where I finished with questions. And my goal here was to kind of present for 25 minutes. And then I guess there's going to be a second session where we can just talk about the app and then ideas that people have about how you might want to use it in class. So that's it.
Excellent. Thank you so much. That was awesome. If you would like, you can keep this room open for another 5 minutes and answer some questions. And I can go open the other room and then you can just make your way over there within the next 5 minutes. Does that sound all right?
That sounds great. I'll do that.
Okay, perfect. All right, I'll go open up that room, but take your time getting over there. Thank you.
I will answer one question before anyone starts. Is like I realize that my links still have my other app, which is called Waves, which does exist, but Google like changed how they do their Google sites, and so it broke my my website, and I have fixed the slopes one, and I'm still working on fixing the other one. So if anyone's wondering why that link doesn't work, that's why. Can I answer a question from Carrie?
Yeah. Thanks, Tim. That was great. Very excited now to see how we can go and use it. My question also when you were going through was, I know that you've got, it's just to clarify, like you've got copies for the mobile devices as in the mobile phone and the iPad. iPad, I'm assuming means tablet as well.
It means actually only specifically the iPad tablet. If it's an Android tablet, which I know those exist, it will run like the phone version. It just won't be as enhanced as the iPad version.
Okay, I think.
But yeah, I haven't done the Windows tablets or anything.
That was my question, because I was sitting there thinking I could see this as a really good demonstration tool as well as for me as lecturing. And did you have a version that ran on the PC? And it sounds like the moment no.
Yeah, each one has its own like programming language associated with it, and to get the graphics to be nice and smooth, like you really have to run it on the machine. So that's the reason.
No, that's good.
I believe. Oh, thanks.
Thank you.
I believe Michael has a question. Oh, Michael, you got to unmute yourself.
In the slopes field, all your tangent vectors have the same unit length. Is there a way to make an adjustment so that the tangent vector's length or thickness might be proportional to their magnitude?
Yeah, so in the slope field one, I didn't do that, and that was because there were no examples that I was seeing about how that was considered to be a traditional slope field. So I know that's kind of odd, but like I didn't do that. But what I will say is that if you're in the phase planes app, which I didn't quite show quite as much of, there's lots of settings in these things. And so there's actually a setting if you go down where you can scale the arrows is what it says. And then you can do that. I could add that to the slope fields, but like I just as I was looking at definitions of slope fields, like most of them didn't have magnitude as part of it. So but yes, so this is how I scale proportionally in the phase plane one, which I did see lots of examples of that when I was building this. Okay, so this is kind of a strange, awkward thing, but like evidently the discussion for this app is going to be in a separate meeting, and so since it's 1 minute to 2:30, I'm going to switch over to that session. So you're welcome to come to the conversations about creative uses of slope session, and that's going to be really informal, just to talk about how we're going to use slopes. Or how people might want to use slopes. So I'll see you there.